Hi, in this video, I'm going to discuss dynamic equilibrium. So equilibrium means net force is equals to 0. And you have two kinds of equilibrium, static equilibrium, which means that net force is 0, but object is at rest, so it's not moving. Dynamic equilibrium is the case that net force is equals 0, but object is moving in constant motion in a straight line, steady motion in a straight line. We know from the property of inertia that you don't need to have any force for the objects to keep moving. Once object is in a motion, it keeps being in that motion, in a constant speed, in a straight line. So from here, you understand that net force equals 0, and the object can be still moving. Let's see. One way is that you could be pushing. Let's say you have a heavy refrigerator or you have some items. You push. Object doesn't move because it's very heavy and you have a big friction. But let's say it starts moving. You could push the object in a constant motion. Just match the pushing force to the friction force, then the object can be not accelerating, not moving faster or slower. You could move the object steady motion in a straight line. In that case, you could be applying the force in a forward direction, and there is the force to the backward direction, push force and a friction force, adding up to be 0. So that's also another example of dynamic equilibrium. So either way, you do not need to have any force that's applied on the object or net force equals 0. Then if the object is in motion, we call it dynamic equilibrium. When you're in a train or fast car, and if you toss a peanut up in the air, and let's say the train is moving in a constant motion at that time, not speeding up, not slowing down, it's moving in a straight line. If you throw a peanut up in the air, where does the peanut land? Does it land back on your hand, or forward, or backward because you're moving so fast? See, fast train can move to with 150 miles per hour. That's 24 kilometers per hour, and also it means 4 meters per second. So every second, it's moving 4 meters. 4 meters. Let's say you throw a peanut. Where does the peanut land? 4 meters behind you, 4 meters in front of you, or 4 meters in your hand. When the train moves, you're moving with the train 4 meters per second. Each second you're moving 4 meters, and the train, and also the air, everything. Relative to you inside the train, everything is all moving together 4 meters per second square. So was the bag of the peanuts and the peanut that's been thrown in the air. Everything just moving at 4 meters per second together. Unless we're acted by a non-zero net force, this peanut don't feel any change in motion, so it's just going to keep going with you. So therefore, it's going to land on your hand. Unless train suddenly stops. So if the train suddenly stops, then where does the peanut going to land? It's the law of inertia, right? Peanuts wants to keep being in the 4 meters per second. but then your train stops. So relative to you, the peanut is going to land in front of you, behind you, or on your hand. That's why we have a seatbelt for the car, right? You're driving the car and you're going fast, let's say, even 25 miles per hour is pretty fast. So then all of a sudden you have to slam on the brake. What happens to your body? Your body was initially moving 25 miles per hour, and all the air in your car was moving 25 miles per hour. And suddenly you slam on the brake. What happens to your body? Your body wants to keep being in 25 miles per hour, but then a car stops. So therefore your body will move forward relative to the seat of the car, and you don't want to slam, or this relative to the car, and you don't want to slam the windshield. That's why you wear a seatbelt. If the car accelerates, increasing speed, your body will go backward because you initially was going slower speed, but the car and a car seat want to go faster. So it's all relative to the motion. And if you don't have any change in motion, you're going to keep being in the same motion. Let's see, I have a video that I can share. I want to share. Here. So here is the video that I videoed it. We're driving a car at night. So you see how fast the car is moving relative to the outside. So you see how fast the light is passing? You see how fast it passes? How fast are we going? 70. So the car is moving 70 miles per hour, and you know you don't want to stick your hand outside the window, right? When it's the car is moving, because you know you feel you're moving fast relative to the air molecules outside. So then anything that happens, you know it's going to hit your hand. Do you feel the same when you're inside a car? Do you feel the same? Here, so then, let's see. How about this? Car is moving fast now again. This time it's really fast. And then I asked my son to drop a ball in a fast moving car. Should I be worried as being parent? Would that ball is gonna hit him with 70 miles per hour? So, one more time, please. Jump it, let go. Ah, nice. Okay, good thing nothing happened. Nothing happened, but let's see. Again. Here. All right. One more time, high, drop it. Thank you, one more time, drop it. Nice. How fast? 80. Oh. So the car is moving 80 miles per hour, and my daughter drops a ball. Should we worry that a ball would hit her with the 80 miles per hour? No, right? It's the ball, her, and the car seats, everything all go together with 80 miles per hour. In fact, Earth, we know now that Earth is moving around the sun. How fast? In order for Earth to go around the sun, it's moving 30 kilometers per second. 30 kilometers per second, we're moving. Again, this is every second, we're moving 30 kilometers. So fast, we're moving. Then, see, I'm gonna sacrifice myself for you guys. I'm gonna bravely stand in front of the wall. Should I be worried to jump next to the wall that maybe the wall will hit me with 30 kilometers per second? So we know that Earth is rotating around the sun 30 kilometers per second, which means each second, Earth is rotating moving 30 kilometers each second. 30 kilometers. Knowing that, I am bravely going to stand next to the wall here. So this wall, and I'm on the ground now, that's moving 30 kilometers per second. I'm going to jump. That there is a chance that this wall may hit me with 30 kilometers per second. I'm going to bravely jump. Nothing happens. The wall doesn't hit me when my legs is detached from the ground. So should I be surprised that a wall didn't hit me? Should I be surprised? No, right? Obviously, we play basketballs, we jump all the time. We don't need to be worrying that things would hit us with the 30 kilometers per second. And that's because not just only the ground is moving 30 kilometers per second, everything all together, every bit, all the air molecules, you, me, leaves, all of these are moving 30 kilometers per second, relatively all together. So that's why we don't need to be worrying. And that's the reason why 400 years ago, people had a hard time believing that actually it's the Earth that's rotating around the sun. How could you imagine at the time that you don't have any fast moving vehicle to really think that, okay, you're moving 30 kilometers per second and we're moving and then like, how can we live like this, right? That was a very hard idea to accept. And but now we know we have a lot of fast vehicles, and it's not a surprise for us. So I hope you enjoy the dynamic equilibrium. Dynamic equilibrium means net force is equals zero. Um, and that's in a steady motion. If you have a net force equals zero, the object is in a steady motion, no change in speed, and no change in direction. And if you want to have and then inertia is the property that wants to stay in motion. Once it's in the motion, when it's at rest, it's going to be at rest. But when it's in the motion, it's going to keep being in a steady motion within a straight line. Unless acted by a non-zero net force, then it wants to resist the change in motion. All right, so that's the end of dynamic equilibrium, and I'm going to see you guys in the discussion.